Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, so we're very happy to have Brent Waters visiting us today. So Brent is a professor at UT Austin and actually also a former Microsoft faculty fellow, and has worked in a whole bunch of different areas. But today he's going to talk about some recent work in indistinguishability obfuscation.
Okay. All right. So thanks, Melissa. Okay. So as Melissa said, I'm going to be. Thanks for everyone for having me here. I'm going to talk about indistinguishability obfuscation for Turing machines, which is a work we did about a year ago or so. Okay, so I want to first kind of, before getting into, I guess the main contribution, some of this work, kind of give a little bit of an overview, or at least my perception of the landscape of obfuscation, which has been a pretty, I guess you could say, hot topic in cryptography over the last 3-4 years. So I would say that the way I look at it, there's three major themes, three major thrusts that you can work in if you're working in obfuscation. The first one is, can we prove it? Can we prove it secure? Hopefully under a good assumption, like learning with errors. There's been different thrusts to try to get there. Nothing's quite settled in, maybe as satisfactory as we want. The second theme, the one we actually, I would say, had the most success in so far, is using and improving obfuscation. That is, if I just assume obfuscation or something like indistinguishability obfuscation is a tool, what are the cool crypto things that I can build with it? Okay. And then the final one is improving efficiency. I think right now, if we ran some of these programs, the sun might give out or something like that. So we like to be able to do better than that. Okay, so for this particular talk, it's going to belong in this sub area. Although, if we want to have some open, time permitting, whatever, open discussion, I have thoughts on these other ones too. Okay, so let's go over at least at a high level what code obfuscation is supposed to be. So the goal is we take in a program. Think of this program as a function, not like an operating system, but just some function with an input. It gives you an output. And what we're going to do is run it through a compiler or an obfuscator, and we're going to get back what I would call a functionally equivalent program. Okay? So two programs, f and g, are going to be functionally equivalent if f of x is equal to g of x for all inputs x. Okay, so that's a pretty simple definition. At the same time, though, we're going to want to make it maximally, we're going to want to make this one as unintelligible as possible. Okay, and we'll get to what we actually mean. This is functional equivalence, a simple definition. What we actually mean by this, can of course vary. Okay, so traditionally in cryptography, getting at least mathematically sound, or what we hope might be a mathematically sound approach to doing obfuscation, has been a somewhat notorious problem. What we'd like to be able to do is just do it for any function you can come up with. And over the past, let's say, 15, 20 years, okay, there's been all these hacky approaches. I won't kind of go into those. But over the past so many years, we're stuck with things like obfuscating point functions or hyperplanes, right? And there's nothing wrong with that, but we have this grand vision of all programs, and then what we like to do, and then what we can do is like, oh, I can obfuscate some point function. There's a significant gap there, right, in what we'd hope to do. The other thing that people have done, though, in the past is things like, well, we can give an explanation of an existing functionality under obfuscation. This is done for like public key encryption, authors there, or re-encryption. But again, I think that kind of misses the target. What I'd like to have is an obfuscator, and I build new stuff with my obfuscator. Not like I already know how to do something and say, oh, here, this is obfuscation if you look at it the right way. Okay. So this changed pretty dramatically with this one paper where we put out a general purpose candidate for obfuscation. This was work with Garg, Gentry Halai, Raykova, Mitsahai, and myself in 2013, where we had, based on these GGH multilinear maps, we actually put out a candidate for one that might work. And there's been different variations on this so far. So right now, we do have some candidates for obfuscation, but what does it actually mean to have a candidate? Okay. So when I first think of idealized, when I first think of obfuscation, the easiest thing in my mind and by the way, anyone just interrupt me and ask me questions. It's obviously a smaller group, so happy to answer anything along the way. The first thing that comes to my mind is some idealized notion of obfuscation, which is that if I give you this obfuscated piece of code, maybe you can't learn anything more about it than if I just give you black box access to this function. So in one world, I give you this obfuscated code, which computes, something, like maybe it does some encryption or does some computation. And in another world, I just give you access to some oracle you can call up on the phone or use some app, and it will. You give it input, it will give you the output. The good thing about this definition is that it's a very natural way to think of it, and it's powerful or natural to build applications. If I can think of obfuscation in this way, and I want to build functional encryption or deniable encryption, you name your favorite. I guess mine is functional encryption, but you name your favorite crypto application, you can probably build it. The downside, though, is that we actually see that there are some contrived counterexamples where there are some functionalities which we cannot obfuscate according to this definition. Okay, like it's impossible to meet this definition. They're kind of built to fail. And I think the problem isn't so much that there exists some, but that we can't really identify where a line should be. For example, you can imagine maybe for this idealized notion of obfuscation, the red is this functionalities we can't do. Maybe the green is what we can do, and it's a very nice, a lot of powerful, good stuff in here. But we don't even have a candidate line. We don't even can say, well, there's not even a good, we know some things don't work. We know some things do, I guess, point functions, and then we can't even explain what might be in the middle. Okay?
Are there any works that say why, sort of black box? I'm not saying they should be black box proofs, but something in the flavor of, well, we can't get a nice classification because, if we did, something else would happen. Or something.
I don't know of any. It's a good question, and I think maybe, it might be good if someone could even put out a candidate. I'm not, say, even if you can prove it, you kind of put out a challenge, say, here's my line, see if you can step over it. I don't, I think that it's a good question. I think the short answer is I don't have a good answer for that question. But yeah, it would be good if there was, some candidate line. Unfortunately, I think most things that are pretty general, you can kind of work in the Barak et al. Result into. Okay, so what we've actually turned to is a definition called idealized obfuscation. Indistinguishability obfuscation, which was actually also put forward in the first paper of Barak et al. And the reason they did it was, I think if you read that paper, I don't know if anyone's kind of read it recently, or read it, they really care about the virtual black box idealized definition, and they're like, this other thing, it doesn't violate, it's maybe not impossible, but it seems kind of lame. That's me paraphrasing a little bit, but and what they say here is okay, in indistinguishability obfuscation, the idea is that if something's a good obfuscator according to this definition, you cannot distinguish between obfuscations of two functionally equivalent circuits. Okay, so what's a functionally equivalent circuit? It's just any two circuits which compute the same thing on all inputs. As a very toy example here, you can imagine A times B plus C versus A times B plus A times C. Okay, these are two different circuits. These are two different circuits, but they compute the same thing. Okay, and then what we want to say here, for if something's a good indistinguishability obfuscator, if O is that suppose for all inputs C0 of x is equal to C1 of x. That means circuit C0 and C1 are functionally equivalent, not necessarily the same circuit. Then it should be computationally difficult to distinguish between an obfuscation of C0 and one of C1. Note that the obfuscator is randomized. Otherwise, this wouldn't work out at all. Okay? Okay, so the good points are that it avoids the negative results of Barak et al. They just don't apply to this. On the other hand, a natural question is is this useful at all? Right? Okay, you give me two circuits, they do the same thing, but you can't tell what they were, but they did the same thing anyway. Who really cares? And I think to some degree that was kind of the attitude of the Barak et al. Paper. But it turns out that somewhat surprisingly, or at least somewhat surprising perhaps a couple years ago, this is the candidate we were able to get. It turns out to be very useful for building cryptography. You just have to work harder than you do in this idealized definition. Okay, and this is where things are not here now, I should be clear, but this is where I'm hoping things will go with indistinguishability obfuscation, where hopefully we can get it built from a standard assumption. We don't have it from LW right now, but I like to think it's possible. And then we can use indistinguishability obfuscation to build most of cryptography, okay, for some vague definition of most. Okay, and I'm going to leave, and we've actually been pretty successful, I would say, down here. And, there's been papers published up here. I don't know if that, but, I don't think we've kind of are yet at the place where I'd like to see us at. Okay, any questions on anything? I'm trying to lead in a little. Okay, so
I actually have a question.
Sure, go ahead.
It's really interesting. Like this indistinguishability obfuscation is so non-obviously a useful definition. So did they immediately realize somehow that this is somehow useful for something?
So the history from it, and actually I'll get into the history in a little bit of slides, a couple slides, is that the Barak et al. Paper in 2001, at least the way I read it, they didn't seem to think it was that interesting. More it's just a technicality, it might not be impossible. But they weren't like, oh, we can do this stuff. Then in 2013, when we put out a candidate, this is what we gave. And then there was actually I'll get to it on the next slide. So then immediately after that, Amit Sahai and myself in a work, we're trying to think, could there be a methodology, kind of a set of techniques or methods for being able to use this? And what we came up with was something called the punctured programs technique. And I won't, I guess I have another talk I'm not giving now, which shows how to build stuff from I/O, shows how to use this. I won't really get into that now. But sort of the general feel of it, and again, we won't see it in detail or anything, is that there was kind of this technique for, you would have this program, you would remove a key element of it, kind of remove some critical element, I should say, in some sense, and it wouldn't change the functionality of the program, so the attacker cannot win without it. Okay. If there's some time later and people are still interested, I could try to sketch up an example how this might work. Okay, and then often for this, we use something. The main tool for doing this would be something called puncturable pseudorandom functions. So a pseudorandom function, usually I give you a key. If you have a key, you can evaluate the pseudorandom function at all inputs, right? So there's something called a puncturable pseudorandom function, which allows you, which is if it's punctured at x star, it allows you to evaluate it at all points except for x star, and then at x star you cannot distinguish the output of the function at x star from something uniformly at random. Okay, so that's puncturable per s, and then using these we're able to build a lot of stuff. So let me give you some sense. Oh.
Does that also imply that you can't tell what x star is?
Oh no, you can give x star out as part of.
But if you didn't, you wouldn't be able to identify.
So Dan had some interest in that problem. Like I guess Dan Bonet recently talked about like kind of hiding where you punctured it. But in the standard definition, that's not necessarily true. And in particular, if you build this thing from the Goldreich, Goldwasser, and McKelly pseudorandom function, you actually very much can see x star because you kind of you have this tree, and then anyway, the tree shows you where it is. So in general, think of x star as being revealed.
Revealed to the guy who has the key, not to anybody who sees the output of the function.
Exactly. So you can imagine you create the master. You create a master key which you can evaluate anywhere, and then you can take that and choose to puncture it at any point. So the points of the function themselves won't really reveal x star. So the points of the function inherently aren't like tied to any x star. But then I say, okay, Melissa, I'll let you evaluate everything except for at a certain point. Okay, and usually, although kind of when you combine it with IO, x star gets hidden a lot, but that's in some bigger thing. Okay, so it seems like, kind of a simple thing. I/O seems like a very basic functionality. This punctured PRF is pretty simple to make just from these trees with pseudorandom generators. This isn't very hard primitive to actually make. But it turns out that if you combine them, and again, not in this talk, but we can build a heck of a lot of stuff from it. Okay? So if we have indistinguishability obfuscation for circuits, like I can obfuscate any general purpose circuit, and I have this puncturable PRF, which is buildable from one-way functions, we can actually make all these very powerful crypto applications. Functional encryption, didn't know how to do this before. Deniable encryption, we didn't know how to do. Broadcast encryption with certain parameters, let's say trapdoor permutations, traitor tracing. All this we can actually just build from indistinguishability obfuscation plus these puncturable pseudorandom functions. So you can build a lot of stuff from it. I guess that's the main catch point. Okay, yeah, and so we've been seeing a lot of these types of papers over the last couple of years at crypto conferences. Maybe program committees are starting to get tired of them, but we'll see. So what I want to talk about, though, in this talk is that here is what we have if our starting point is I/O for circuits. Okay, so you give me any circuit, function encoded as a circuit, and I'll obfuscate it. And pretty much size of my obfuscation will scale with the size of the circuit. Instead, we could ask, well, what if we could, from I/O from circuits, we could build I/O from Turing machines? Okay, what other applications could we get if we had obfuscation, indistinguishability obfuscation for Turing machines that we don't get up here? And there's actually quite a few things that you can build. For example, time lock puzzles. It's got a little cut off here. Delegation of computation. Functional encryption for Turing machines, constrained pseudorandom functions, and low overhead obfuscation for something like that. So you can build a lot more things if you're working in the Turing machine model. And what this talk is going to be about is how do we get this arrow coming down from here.
What's a constraint PRFs?
Oh, it got cut off. Constrained PRFs for Turing machines. So you could write a lot of things. What is a constrained PRF? Okay. Never mind the Turing machine part.
Yeah.
The puncturable PRFs is a special case of constrained PRFs. Mm-hmm. So imagine that I choose a key for a pseudorandom function, and I say, okay, Steve, I want you to be able to evaluate only on a certain subset of these. So I imagine a predicate. Let's say so I have a predicate function in my head, and I say if f of x is true. I'm going to give you a key such that if f of x is true, you can you can evaluate it. Maybe the function is, does the string Steve Myers appear as a substring or something, something funny like that.
But the predicate's on the input, not the output.
On the input. Yeah, the output should be pretty much randomish. So for a constrained PRF, I could do it. So there's some function attached to a key. You can evaluate to everything for which the function output's true, and everything else should appear pseudo-random to you, more or less. And then you could have that for kind of where the function was a circuit or the function was a Turing machine. Is that good? Any other questions?
Guess what's time lock?
Oh, okay. it's a problem with having one of these slides. You open yourself to 10 questions. So a time lock puzzle is one of these things where if I put in a certain amount of computation, I can get out an answer. And the trickiness with those things is to be able to get them so that parallelization doesn't help you. So with random oracles or hash functions, you can kind of build these heuristically. But if you get 100 computers, let's say Microsoft's much more power. We want Microsoft to meet to be on even footing or as close to as possible. If they buy 10,000 computers, they can do it 10,000 times as fast. So we want new candidates for making it needing to be serial.
But so you've actually you have some construction that if you have this I/O for Turing machines, you can do these time loop puzzles. You have a construction.
Yeah. There's another paper for that. It's there's an app for that. There's a paper for that.
Is it possible to explain somehow intuitively how that kind of thing can happen? So I don't understand at all how this I/O can lead to something like that.
Can lead. Well, how about this? In showing this arrow, I'll show some of these techniques for I/O. Probably touch on some of them a little bit. Possibly after the talk, I'm happy to go into one of these things. In some sense, it's almost a different talk, but I could give like a simple example for public key encryption from symmetric key encryption. Maybe afterwards, if anyone. How many people have seen that? I'm just curious. Okay, so a decent amount of people. Okay, so using the punctured programming, blah blah blah. Okay, but yeah, maybe afterwards I can divert a little bit. Okay, so here we go. So we want to have indistinguishability obfuscation for Turing machines. And again, let's just briefly go over what the difference between circuits and Turing machines. So a circuit is good because it's a general model of computation. I have and or not gates, let's say. So it's good because it's general, but the description scales with the maximum computation time and space. Okay, so I might have some program, for example, which is like find the first billion primes. The description of that program could be pretty small in order to do this, but the circuit description for doing this would be quite large. Okay, and then so I actually looked up. I found a Turing machine online. It was kind of cool to see it in action. It turns out they don't go that fast when you do them mechanically. But so in a Turing machine in general, the description of the program might be much less than the computation. Okay, so we're going to think about programs described as Turing machines. Okay, and the reason we want to maybe do obfuscation in terms of the Turing machine model, where my program is a description of a Turing machine or just some program as opposed to a circuit, is that, well, we can get this efficiency of encoding, and we can get just some of these other applications that I referenced earlier. Okay. Okay, so people have looked before at doing Turing machine obfuscation from circuits via building Turing machine obfuscation from circuit obfuscation. But what they needed before in the past was some stronger notion of some stronger notion of obfuscation, stronger than this indistinguishability notion I just talked about, something called differing inputs obfuscation, also proposed in the Barak et al. Paper. And what this says is that if an attacker can distinguish between programs P0 and P1, then it must know some X where they're different. Okay? Now, before, for indistinguishability obfuscation, we said we were only concerned about programs which were the same, functionally equivalent, the same everywhere. Here, these programs could be different, but you need to know where they're different. And there was, I'll just kind of cluster these all together. There's been pretty much different sequence of papers that kind of led to showing that, well, if we have this for circuits, plus something called SNARGs, zero-knowledge proofs, succinct zero-knowledge proofs, SNARGs, we can get this Turing machine obfuscation. The problem, though, with different inputs obfuscation is that it looks like it might fall. Remember we talked about this impossibility result of Barak et al. It looks like there's not absolutely an impossibility result yet, not like some nail in the coffin bad, but it's starting to look like it's closer to the VBB side, where we can come up with functionalities that are impossible to differing inputs obfuscate. So, for example, there's this paper by Garg, Gentry, Halevi, and Wicks that appeared at Crypto 2014, which gave a conjectured function of things that you couldn't DIO obfuscate. And then at this last Eurocrypt, with Mihir Balarian and Igor's Stepanovos, I had, I also, with them, I had a result putting something like this under more concrete assumption. Okay? So if I had to take my bet, differing inputs is kind of going the way of VBB. Okay, so what we want to be able to do is get something from I/O. Okay, so that's the point here. Okay, so in order to do this, we're going to kind of think. Here's going to be the general framework for doing it. In general, what we're going to do is we're going to use circuit obfuscation instead of obfuscating the entire computation, like we did before circuit obfuscation. I'll use circuit obfuscation to sort of do a Turing machine step. I think a Turing machine is a description M. It takes as an input, takes as its internal state, and then outputs something to the tape and moves along the tape. So that kind of mechanism we're going to put in some type of obfuscator, and we're going to store this bigger state on the outside, not in the obfuscated program. And what we're going to do is pretty much run this obfuscation. So before our work, or I guess what appeared just like right before, like a month before, kind of right before our work, was some works which I'll call that give an entire state programming approach. So at a very high level, let me try to tell you how they do things and how they prove things. Okay, so what they're going to do, imagine this is just the Turing machine evaluated on one, let's just pretend we're looking at it on one input for simplicity. What they're going to do is they're going to try to do the computation on an input and hide how it was computed. Okay? So originally the computation starts out in some start state and then it just does the computation. Now what they're going to do is that they're going to have a hybrid game where t is, let's say, the time step, where in the hybrid game t they're going to pretend, sort of simulate or pretend, not really do the computation up until step t. So this gray is my notion of pretend. So it's giving some pretend signal, not really doing the program. And then at step t, they're going to program in what the state of the Turing machine, what the state of the Turing tape should be, what the configuration of the computation should be. And then they kind of run it honestly from then on out. Okay? And what they want to show is that that you can't distinguish game t from game t plus 1 for all t. Yeah?
Should I think of the tape as stored as like a bunch of encryptions?
Yeah, roughly at the level of that I'm explaining it now. I think that's fair.
Okay.
Yeah, so a bunch of kind of something encrypted. I'm leaving it pretty vague. But yeah, when I go into my work, I'll try to give a little more detail than that. Okay, yeah. So yeah, in particular, it has to be encrypted in some way because you shouldn't be able to tell pretend from real, right? So what we do is we initially start where everything is like kind of the one is this. Initially, we just program the initial configuration at time step 1 when we're doing our proof. And then we want to gradually move it so it's pretend, 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 pretend until we hit the very end of the computation, t star, and then we just program in the output. And if we're just programming in the output, intuitively, we're not seeing how the computation was done. I understand this is pretty high level, my explanation of this.
Yes, so by this you mean that you're somehow, when you're building this, so you have this obfuscated program that's just the little Turing machine step, and now you're going through these game hops where you're changing the program slowly, and you're going to manage to change it so that it spits out different states.
Yeah, so I'm kind of changing the internals. The problem is I have this at such a high level because I'm capturing 2 results. But internally, along this game, so where I have it t here, let's say I change so originally the program starts at time step 1, and now the program says, okay, I understand I'm just going to be fooling around or pretending until time step t. It kind of is aware of this. And then we want to push it to the end where we just program the output. The salient point here, and there are 2 ways of doing this, and this is why I have it pretty vague because I'm trying to capture 2 things there. There's this, so independent works of Patansky, Garg, Lin, Past, and Talang, and Kennedy, Holmgren, Jane, and Vaikunth Nathan, where one did with Yao garbled circuits, one did the computation on the inside and then signed some state, like kind of sign what was going on between these things. But what I want to point out, the key point in comparison, let's say, to the work I'm going to talk about, is that their program. So when they encode, remember the whole point of doing Turing machines was that my encoding time for obfuscation and the size of my obfuscated program should grow with the size of the program and be independent of the time and the space to compute the function. Okay, that was the point of not using circuits. Yeah. Now, so instead, what they had was they got that for the time, but their the time to obfuscate grew with the maximum size. Okay, and I say, okay, well, why did it grow with the maximum size? The point here is that I said, well, you're going to fake, and then program in the proof, and then program in what the state of the computation is. Okay. Well, if your Turing tape grows this long, you could try to scale my arms somehow. If it grows this long, up to some maximum size, you have to have some mechanism for programming that in when you're creating the obfuscated program. So you need your obfuscated program in order to program in it at an arbitrary time period. You need your obfuscated, the whole big package when you obfuscate it to grow as much as the Turing tape might go. Okay, and you can ask, well, is this a problem? Well, I don't know. I mean, if your memory stays very small, even though the computation's big, maybe not a big deal. If you might have memory that if you have an application or a function where the memory usage grows roughly proportional to the time, it doesn't really buy you any win over the circuit approach. So the answer is it really depends on what you're computing.
So does the obfuscation definition work over like complexity classes or something? Like you say, like we're going to obfuscate n-cubed timeout Turing machines, or
okay. That's a good point. I've been let's see. I've been being a little loose from that. So usually for circuits, we say stuff like we can obfuscate any polynomial time circuits. So here we want to be able to here for Turing machines. Well, I'll give you a precise description of what performance results I want to have. Roughly, think of it as I want to be able to obfuscate any Turing machine M, just any Turing machine computation, and that the size of my obfuscated program should grow polynomially in the security parameter and the description of M.
Okay. So here's the what I'm trying to understand is, let's say I have a really crummy implementation of a functionality, and it takes like order n to the 10 time to compute.
Okay.
And then I have another one that's good, and it takes order n squared to compute. Now, when I obfuscate these things, the running time, if the definition doesn't sort of say I don't have to
okay.
the running time somehow, then it seems to me that you have to have the worst possible algorithm as the obfuscated.
Okay. Okay. Good point. Okay. So. So you do need to take as input like a maximum running time. Okay. And okay. No, that's fine. Yeah. So you're saying you could distinguish between them if you just saw one just finish faster. Yeah. Yeah. Okay. That is correct. Yeah. So you have to. So yeah, when you obfuscate, you also declare some time bound, and
anything that's slower than that, you're saying.
Yeah.
Distinguish, but we don't care.
Yeah. Exactly. And usually when you're using these in crypto, there's similar programs, and you can see that. Okay. No, that's a good point. Yeah, when I glossed over a little bit. Okay. Okay, so kind of getting back to their proof, because they program in the entire state, this kind of memory restriction seems to be inherent in their technique, not just some detail. Is everyone okay up until this point, or any questions? So this other work has this thing where the circuits grew with time and space, and now and we wanted it to be just program size. Now it's program size plus space. So what we want to do is just get it with program size. Okay. So the question is, what can we do differently? And here I'm just going to try to illustrate it a little bit at the high level our approach. So I'll first give a high level approach to what we do. Then I'll focus in on a more narrow program, which would be kind of the core techniques that we do. So what we're going to do is for the big problem of Turing machines, we're going to actually turn things around. That instead of in our main hybrid, instead of kind of doing fake program and everything, then do it for real, we're actually going to go from the opposite end of the computation. We're going to do the computation for real. Then we're going to start faking. It's almost kind of the opposite. And we're going to start at the end where we hardwire in the final result, and then kind of make it fake, let's say, only for the last step, and then only for the last two steps, and then all the way to the very beginning. So the proof will actually just visually in the final product move in the opposite direction. We have the gray first. We have the blue first, and then the gray. Okay, so let's see how to do it. So actually, how to do it, we're not going to get to this backwards hybrid yet. And what I want to do is I want to spend most of the remaining of the technical portion of the talk on a smaller target that I'm going to call message hiding encodings. So let me explain to you what I mean by this. It's a pretty simple concept. So what I want to do is I want to encode a message that can be recovered if m of x, remember, m is a Turing machine, if m of x is equal to 1. So I'm going to pick a particular m, pick a particular x, and and output it if it's equal to 1. Okay? Now, at first it might, so what should happen is you should get the message, and what we want to have is that you get the message if m of x is equal to 1, and if it's not, if it's false, equal to 0, you shouldn't learn what the message is. Okay. Now, the first thing that should come to your mind is it's pretty easy to do this, right? You just see if you have m, you have x, you run it, you see if it's equal to 1, and you output the message. This is, if it's equal to 1, if it's not, you don't output the message. The trick here is that we're interested in problems where the encoding time might be much smaller than the time to actually compute the function. So you can imagine, like, you know, I want you to get the special message if there's a trillion-digit prime, you know, ending in 35. I mean, something like that, where I could encode that statement very quickly, but actually finding it could be could be time intensive.
EBE, what you do?
What?
And she's like an EBE thing, so you just encrypt it. Oh no, never mind.
Yeah, like ABE, yeah, there have to be some key given out and all that stuff. Yeah. So what we have is we have a messaging. So this has two algorithms. One is called the encode algorithm, which takes as input security parameter the message m, x, a maximum time-bound t, and the message. Okay. And it outputs an encoding. And the second one is the decoding algorithm, which will take in these almost the same things, but also the encoding. And it will either output the message or bot, same failure, it did not work. Okay? So what we want is correctness is basically if m of x is equal to 1 within, and it's equal to 1 within t steps, capital T steps, then you should get the message. And for efficiency, let's just think of capital T as 2 to the lambda so we can kind of ignore it. We want the encoding time to be polynomial in this machine description and log of capital T. Okay? Whereas the decoding time could actually be polynomial in how long it takes to decode it. Okay, so that's the main difference. In general, we think of T star as being much bigger than log of T. This is why the decoding can take longer than the encoding. Okay? Melissa?
So that's not a requirement in the sense that it's fine if some inputs you can decode very quickly.
Yeah. I mean, if it's like totally obvious, yeah. So it must be at least that. You mean you could decode very quickly, or?
Yeah. So I was thinking, like, does this give you like a time lock puzzle automatically, and no, because you're not lower bounding.
Yeah. No, it doesn't. Like, if it's true, and you have some super shortcut way of getting at it, it doesn't violate security. Like, there might be like the way you're supposed to go, and then this other way, and it's okay if you can go faster. At least according to this definition. Okay, yeah, and so for security, security is really the property is only defined for when m of x is false. Then you shouldn't be able to distinguish whether encrypted message 0 or message 1. Okay, and it turns out that this is good enough for delegation, witness encryption. Time-like puzzle, you need to combine it with another primitive, so it doesn't immediately, to answer your question, it doesn't immediately give you time-like puzzles. You need to combine it with something else. Okay, so you need to do a little work to get time-like puzzles. Okay, so in order to do this, what we want to do is, essentially, if we're trying to do these message hiding encodings, at the kind of intuitive level, there's kind of the right computation you're supposed to be doing, right? Like, you know, we'll have some state on the outside. We'll have an obfuscated Turing machine step. What we'll see is we'll kind of feed it in. We'll feed it in, get out some update to the state, sign that, feed it in again, and keep on going and going. And what we want to make sure is that intuitively someone can't kind of divert our computation away from where it's supposed to be. We want to use the properties of I/O to make sure that the computation is done honestly. And only at the end will you get the message of m of x is equal to 1. So what we're going to have here is, in order to do this, we're going to have some principle called selective enforcement, which is going to get around this sort of semi-paradox we'll see. So this obfuscated program, that's a circuit, so this subcomponent that's doing the obfuscated Turing machine step, is going to take in there's going to be some larger tape memory, and then there's going to be the obfuscated program, which will take in something much smaller than the entire tape, right? Now, so what it's going to do is it's going to take in a small commitment to the entire tape as part of its input. Now, at the same time, though, to get I/O to, remember, I/O only works in functionally equivalent programs. To get I/O to work, we need some type of perfect binding property. So what we need is we both need a small commitment to a large memory, and it seems like we need that small commitment to be perfectly binding for that entire large memory. And if you look at these two goals in tandem, I don't know why I picked this out. It's like James Van Der Bee. Anyone used to watch Dawson's Creek? I didn't even watch it, but anyway, he's crying. And he's sad because these things are kind of in conflict. You can't have a small commitment to a large memory and have it be perfectly binding. Okay? So the idea here is that we're going to kind of relax the goals, where when we're moving along certain, we can't be perfect with a small accumulator, with a small commitment, we can't be perfectly binding commitment to the entire memory at one point, but you could be perfectly binding to one location, right? Sorry?
Can you explain a little bit more why it would intuitively need to be perfectly binding? Like, what does the binding of the commitment have to do with the...
Oh, okay. So it's kind of a high level. Okay, so the definition for indistinguishability obfuscation must be that that I can move from one program at some point in my proof. I'll move from one program, kind of hardwiring in things in a certain way, to another program, and I can use that definition to do this. If and only if these two programs are actually functionally equivalent. Like there's no input on which they would differ. Okay, so you could imagine what one attacker might try. What one attacker might try to do is, if the real, in some sense, what was supposed to be written at input I on the tape was symbol A, and it might try to get you to pretend that it was symbol B. Some other symbol B instead. Now, suppose you try to enforce that, but only a computationally binding commitment where there existed a proof, there existed a bad proof. I couldn't use I/O to do this because there would exist. Sorry, I know this is kind of high level what I'm trying to get across. But it turns out that in one case, if it was perfectly binding, there was just no way that you can make location look like it was symbol B instead of A. If it was computationally binding, it should be computationally hard to do so. And for these for two programs to be functionally equivalent, if I can say, well, this program would only work if the symbol was proven to be A, then I can kind of move it somewhere else. Where if it was computational, I couldn't use I/O in that step.
So the issue is that you want to do these game hops, so you change between different programs.
Uh-huh.
And you can only argue that they're functionally equivalent if you know that a particular input is what it's supposed to be.
Yeah, the only way to, let's say at tape position I, for this accumulator value at tape position I, it could only be legitimate, you could only give a proof for symbol A. That is the only possible way. Versus, in a computational thing, you could say it would be computationally hard to do it. Now, if you had DIO, if you had different inputs obfuscation, you could actually use the more relaxed version of that. I know it's not the best. In some sense, you have to look a little deeper into to see exactly. Does it give you some intuitive idea, or am I? Yeah. So the problem is, it seems for IO is harder to use than different inputs obfuscation. In different inputs obfuscation, you can use things like these computational commitments because you can use this extraction property to kind of extract a collision or extract a false proof and break something. Whereas I/O you can't, so you need this perfect. It's kind of harder to use.
So this is because like in one circuit or something, you'll be say checking the proof, and in the next circuit you'll be checking the statement that you're proving or something like that.
Yeah. So yeah, maybe in one circuit, it's been a little while since maybe in one circuit you're checking the proof, and in the second circuit you're just saying fail if symbol wasn't A. Yes. So these two are functionally equivalent if the only way for the proof to go through was that. This is a very good question. So let's say in one circuit I'm checking the proof, and in the second circuit I'm saying fail if it wasn't A. Well, if the only way for the proof to go through was for the symbol to be A, these two are functionally equivalent. If there could have been a different way, they're not functionally equivalent circuits. Does that help? Or, okay, good. Now the problem is, yeah, kind of going to this thing that, yeah, it seems that I need perfect binding to get these I/O type proofs to go through, but I can't just do it for the entire memory at the entire time. So what instead we do, our idea was that we're going to, in the hybrid at time step t, if it's looking at position I only need to be binding for what that one memory location was. And then later on in the computation, I don't care about being perfectly binding everywhere. I just care about being perfectly binding here. So what we do is we have this tool which we're going to call positional accumulators, which allows you to be binding to different places at different times in the proof. Okay, so I'm going to, it got bored of me. This might be a Melissa deal, yeah. Well, it was her question, so. Okay. Okay, here we go. Okay, so so to do this, we're going to have this tool. Let me just, since time is low, let me just kind of go over some of the tools that we use to put this together, and I can try to answer some further questions offline. This tool called Positional Accumulators. This is a simplified version of it. So let me try to explain what it is. So there's a setup algorithm which takes as input security parameter and the maximum size of the tape or the memory, and it outputs some public parameters. ACC 0, this is initial, and store 0, this is initial storage. Object, this is initial commitment to the storage. So think of, eventually this will stay small and this can get big. Okay, that's the way to think of it. And then there's also an alternative algorithm which I call setup enforce, which says it takes in an index I star between, let's say, 1 and t, or 0 and t, and it's perfectly binding at position I star. Okay? And then there's like, what I call it prep, but it's more like a read storage and give a proof, read storage at location I and give a proof and find that it'll output its message M plus a proof that it was at message M. Think of that prep algorithm as doing that. And then there's kind of a write or an update algorithm which will take as input the storage index and a new message. Okay, so this is so think of this as the big storage, and I can write to a location, get a proof that I did it correctly. I can read a location, get proof that that's done correctly, and then do a write. Okay, and then you can also, again, I won't go into too much, you can also update your accumulator. When you do a write, you can update your accumulator for a new commitment to that storage. Okay, so we want certain efficiency conditions for here. And kind of, here's the important security property. Basically, you can't tell if I'm perfectly binding to index I star, you can't tell whether I'm perfectly binding to index I star or index I star prime. Or put another, you can't tell from normal setup from this. Okay, so if I am perfectly binding somewhere, you can't tell where I am perfectly binding to. Okay, and then we want it to be perfectly binding there.
And the verification is all with respect to the accumulator. So you don't store anymore when you're verifying, you just, is that right?
Yeah.
So you verify this proof by...
Yeah, it's done with respect to the accumulator. Yeah, there were like 7 algorithms, so I think I cut some of them off. But yeah, so the verify will be with respect to yeah, you're right, it has, with respect to the accumulator. Yeah, good point.
You don't need to have a big store, you just have to...
Yeah,
small
so this subcomponent that's doing the Turing machine steps will take in the accumulator at each time, but it won't take in the whole storage. And then it'll take an accumulator, the claimed input at a certain, well, I guess it's here. So if we look at the computation, here's what we're going to have. We're going to have this big state from the outside, and here's what it's going to, and the smaller, even though it doesn't look small on the screen, the smaller obfuscated program. Okay? So the storage is going to be the whole storage of everything written into the tape so far. That's going to be the big thing. The accumulator, which is commitment to the storage. On the outside, we're going to have the current time step, the current position, the Turing machine state, something called an iterator hash. Let's not just kind of a hash on all this. Has some other I/O type properties. Let's not worry about that. And then what I call a signature on B through F. Okay? And it's a special thing called a splittable signature, but again, we'll...
The D and E are encrypted or something? Somehow hidden. They're not. Do you know the position?
Well, since we're only doing message hide, so we're doing the simpler thing of message hiding encoding,
Okay.
which we're only hiding the message. We're actually not yet hiding how the computation went. But then this will bootstrap to that. But yeah, so in this primitive, you can see where you're going. You can see the computation. Okay. Okay. So pretty much what happens is, okay. So that's my obfuscated thing, and then when I'm decoding it, there's really just these steps where I read from the accumulator at whatever position I'm supposed to be at. I pass B through G, kind of shove that all into this circuit obfuscated program. Importantly, I do not shove A in. I do not shove in the big storage object. Okay, otherwise I'd be back to where these other results were. Okay, so I only shove in small stuff for some definition of small. So not the entire state, not the entire memory yet. And then the obfuscated code will do stuff like it'll check the hash, check the signature, check the accumulator proof. It will perform a Turing machine step, get an update, have a new accumulated value, update the hash, and then sign all that. So it kind of just signs it to itself. So we keep on taking all this stuff, shoving it into this obfuscated code, having it do a Turing machine step, and it outputs the next commitment and the next state and a signature on that. So that's how the whole, that's kind of how the process goes. And then, yeah. Okay, so yeah, I'm kind of running low on time, so I'll just try to more give a high-level view of the proof. So pretty much we imagine if someone actually is evaluating this message decoding algorithm honestly, doing what they're supposed to, there's a sequence of accumulator, position, state value, signature values that comes along out of that, all the way from the beginning to the end. And pretty much the hybrid, at hybrid step T, so here I'm going to be starting at the beginning and working to the end. What I want to do is initially, at the very beginning, I know that I can enforce that the first accumulator is 0. That's just kind of my accumulator star of 0. What I want to do is say, well, you're only getting a good signature. The signature will only, at time step T, somewhere in the middle now, you're only getting a valid signature if the accumulator value is what it's supposed to be. So I want to move from like being certain about what it is at the very beginning of the computation to being able to hardwire in it only works well at this point in the computation, and then one more and one more and one more until we get to the end, and you only should get the message at the end if you're using the honest accumulator value.
By that you mean the thing that was produced by the previous.
Yeah. Well, there's an honest transcript, right? So kind of think of this as the accumulator as this is the honest transcript of what's supposed to happen. And initially, this obfuscated program can know like what the starting state should be. It could hardwire and say, this is the only good starting state. What I want to do is I want to move the proof to like where now at time step 1 and now time step 2, 3, 4, up to 10, whatever, that I have hardwired in. It said in the program I hardwire in, well, if I'm at time step 10 and I don't see this, I'm just quitting.
It's deterministic.
Yeah, it's deterministic, yeah. So I want to hardwire that in. First it starts at time step 0, and I want to move that all the way to the final time period, where if I don't see these inputs, I'm quitting. Okay, so you have to program in that awareness into the obfuscated program, which isn't initially there. So you program in what actually it should be. So you kind of move it along until the very end, and then it should know what its state is supposed to be at time step T star, and that will. And if it's supposed to be 0, it won't give them. You can get rid of the message.
Does that not take size or space? Do you not need a
Oh, okay, good.
space in your circuit to store all those?
For up to T star?
Yeah.
Well, all these things are short, right? No, okay, no, here's the point. Okay, good question. So first I hardwire in what's supposed to be at time step 5, right? Now I want to hardwire in what's supposed to be at time step 6. I want to erase also the hardwiring for time step 5. Yeah, so yeah, if you hardwire it in all the way through, then your obfuscated program bloats. And when I was first trying to attack this problem, kept on happening. So yeah, if you don't kind of erase the previous hardwiring.
But this is part of the proof, not part of the execution, right?
True, it's part of the proof, but if your proof needed to hardwire in all these things to get the proof to go through, kind of you would have to
No, I understand.
you have to make it bloated.
But what I'm saying is you don't need to keep these hardwired values in when you're actually executing.
Oh no, when you yeah, these only exist in the proof.
Right. Okay.
Yeah, this hardwiring doesn't happen in the real thing, but in the proof, yeah, you have to be able to keep on hardwiring and hardwiring one step further, plus erasing what you used to hardwire. If you kept what you used to hardwire, you're toast. You didn't solve anything. That was your question, more or less. Okay, yeah. So that's the tricky part. Like if you could keep it's an easy proof to get through without that caveat. Okay, so there's these main substeps. I'll kind of hand wave a little bit here. So you start at hybrid T where you only produce good signatures if the input to step T of accumulator T minus 1, so you kind of only output a good signature if the input to accumulator star of T minus 1 is this particular value. So let's say that's for... Now what I want to do is I want to move to an intermediate hybrid where I think of what the output accumulator value is supposed to be, and I hardwire based on that. Okay? And this is where the selective enforcement comes into play. I was talking about like where it has to be perfectly binding at a certain step. Okay, so I'm hardwiring in for the input memory commitment. Now I'm hardwiring on the output, and the reason these two are equivalent is because I'll have things set up such that they're functionally equivalent. And then what I do is I kind of changed, instead of hardwiring at accumulator T star from the output side of step T, it'll be the input side of T plus 1. Okay, so for that first little arrow, let me go through this quickly. So for this first little arrow, to get this first arrow to go through, I need things to be functionally equivalent. And however, the problem is that for any particular accumulator value, there could be many possible symbols. It may be hard to find, but there could be many possible proofs opening up to it, which is the problem we were talking about earlier. So the idea is when actually doing that big arrow proof, what I first do is I first change it to be binding at the position I'm looking at, and then I do the IO step. So first to change the accumulator to be binding here, and by the fact that you can't tell that I'm binding at this position, the adversary should win with the same probability. And then since it's binding, I can change that internal hardwiring. Okay, so this is what I call like an IO-friendly tool, this positional accumulator. It lets me make that move. Okay, so yeah, normally there could be many possible openings, and then I change it to be at this position. Then I change it to be selectively enforced at this position, and only the right one can be opened, and you can't. It's just impossible. By this point, if the attacker wasn't able to tell that you made it selective enforcement, now he cannot open it to something different. Okay. Okay, and then for this external change in wiring, I won't get into this. There's a fairly straightforward path using complexity leveraging, using sub-exponential hardness assumptions to do this. We decided that we wanted to do the more macho way without sub-exponential hardness assumptions. I'm not sure it was a good idea. Maybe it was like kind of made it much more painful. Anyway, so we introduced these things called splittable signatures to do it. We forked off kind of a lot of kind of messy stuff kind of goes on underneath the hood. Anyway, so we do it without sub-exponential hardness, but it could have been done easier if we just used that. Okay, so great. We're towards end of the talk now. At the beginning, I did talk about this whole backward simulation deal. We haven't seen any of that yet, and don't worry, I won't subject you to that. But the main idea is that in the message hiding encoding, you can see how the we talked about. I think one question was we can see how the computation goes, right? If you want to then do one step further, of randomized encodings where you can't distinguish between a message a machine M0 and M1 that can compute two things, you have to add on a little more to this. In particular, we start with an oblivious Turing machine where the Turing machine tape head movement is independent of the computation. The symbols that are written to the storage should be encrypted, so you can't see what it's writing. You can't tell the computation from that. And then what we kind of do is you sort of combine with these new ideas, you kind of combine the proofs that we used to have. you kind of use these techniques that we just saw to anchor what the output must be at step t, then you kind of erase it, then you kind of anchor it again using the techniques, then you erase one more. So if the hybrid is t star total, if the computation takes t star steps, there's actually there's kind of O of t star, there's like a quadratic hybrid that comes in.
That's because you're merging the previous proof.
Yeah, exactly. Like, yeah, to just erase one symbol, we have to do that entire proof. And then to erase one more, we have to do the entire proof again. Okay, this is not an obfuscator. In case that's big O notation. In case anyone. Yeah, so exactly. So we kind of, for each erasing step, we need to do this entire proof again, basically. Anyway, and then once you have these randomized encodings, it's pretty simple to go to Turing machine I/O. I'll just state that as a fact. You kind of think of randomized. Anyway, I can go over that afterwards if anyone has any questions. Okay, so in general, the point was to actually do the computation, avoid this whole state programming, and then we could get this Turing. We can get Turing machines for I/O, which was our goal, and not just circuits. And one of the main ideas, I guess, that we saw, we didn't see too much of this, but was that I/O makes you work harder than different inputs obfuscation. Different inputs obfuscation, if it's a computationally hard task, you can kind of use its extraction property to see, to get a break of it. Here we needed to build these kind of so-called I/O friendly tools where we selectively enforced at just this one memory. So initially it's computationally everywhere. Now you can't tell, but now I'm perfectly binding here. And that allows me to change my hardwiring. Okay, and then I'll just mention there are a lot of works that kind of built on it. Was, I guess, with Allison Bishop, Venkata, Koppula, and myself. Okay, so I should, sorry. At the end of the talk, I mentioned I had co-authors who were Allison Bishop, former student, now professor at Columbia, that's right, and my student Venkata Koppula, and so a lot of works ended up building on these techniques, which was kind of one cool, more than just the result, it was cool to see that it was used for a lot of other things. Okay, so thanks for your time and for everyone coming here.
Are there any additional questions?
Okay. Sure.
Could you, maybe this will be better after anyone else has any questions, but could you just, the thing you mentioned in the beginning was the punch hole encryption thing? What?
Punch hole PRFs.
Yeah, so there's you can have a function where you remove some critical.
Oh, like how to do something with that?
Yeah, well, could you show an example?
Okay, let me see if I can bootstrap the public key encryption one up in my
So that
head.
was an example of how to use it or how to construct it?
How to construct it. I'm just trying to think of like what.
How to make the punctuable PRF.
Yeah.
Oh, okay, that's actually easier. Okay, good. Do you have a marker, or does anyone?
Isn't that a service?
I'm not so fast on my PowerPoint. Oh, okay. Oh, so there are some markers behind here. Are you familiar with the Goldwhite, Goldwasser, and McKelly PR? Oh, okay. Let me just sketch it really quick. I'll sketch a three-bit example. So let's say we have a pseudo-random generator from n bits to 2 n bits. Have people seen these puncturable PRFs? Okay, so maybe I'll sketch it really quickly. So you start off with, so normally for a pseudo-random function, let me just make it 2 inputs. We'll have some seed S, and then we'll apply G to get S sub 0 and S sub 1. And then we can apply the pseudo-random generator. So we think of this as an n-bit string, and we apply it to what's called a pseudo-random generator. And can you see this even? Okay, and we get two n-bit strings out, and then we can apply it again and get S sub 0, 1, S sub 0, 0, S sub 0, 1, S sub Okay, so you can keep on doing this. Let's pretend I only have 2-bit inputs to my pseudorandom function. Then so my secret key is S, and and the output for the input 0, 0 is this. The output for the input 0, 1 is this. 1, 0, 1, 1. Okay, and if I had an n-bit string, n-bit input or l-bit input, I just take this tree down L. And notice that, wow, the total number of things goes exponentially. I just have to start from here and trace down one path. So it's pretty fast to evaluate. Okay? Now suppose I wanted to give you a key that could only evaluate everything except for 1, 1. So it's punctured at 1, 1. So what I can do is I can give you, so I don't give you this because this will allow you to get everything, right? So what I do is I go down, I kind of give you all siblings. So I think of the path to 1, 1, and I give you all siblings off that path. So I'll give you this, which lets you get everything below. I don't give you this because I can give you that, but I give you this. Okay? Now, this doesn't look too much more efficient than just giving you all inputs when it's a level 2 tree. But if it's a level L tree, it's the difference between giving out 2 to the L things versus L things. So that's the punctuable PRF. Okay. Okay, so that works. So yeah, the construction is pretty simple. Steve, you?
So yeah, I'm not super good at these definitions in terms of playing with them and thinking about them, but it occurred to me during this talk, so if you have an obfuscated TM, the definition is sort of like a passive, it's sort of like CPA security. It's if you run the obfuscated Turing machine, you're guaranteed not to learn anything observing it, right?
Yeah, you can't distinguish between any. The construction didn't get into it, but can't distinguish between obfuscation of machine 0 and machine 1. Yeah.
Right, but what if you let's say I screw up the state in the middle of the execution, and then is that permitted? Like, is it here's the transcripts and I just look at it, or is it I run the?
No, it's definitely permitted because. Remember, I'm going to give you an obfuscated. I'm going to give you an obfuscated either of machine 0 or machine 1,
okay.
And you have that code. I can't say, oh, I don't have a definition that says, oh, well, you can only do this with it. Like you can do as an attacker, you can do anything you want. So you could kind of, as part of looking at it, you could run it to this, try to do something else to it.
And verifiability directly from these then.
Define verified code.
Like if I somehow, I want to make sure I'm running the code. The obfuscation is an obfuscation. So you're giving me code to run. It's an obfuscated code. I like to actually know that the functionality that I'm running is one that you told me you're going to run.
No, you wouldn't know. And in fact, to some degree, the definition of it would be that you couldn't tell. So
not really, because you're saying that you're saying that I can't distinguish this functionality from this functionality, and so in principle you should be able to say, but yeah, I know that I'm running.
I mean, I could combine it with a NIZK, for example. Like I could prove to you I formed it according to these rules.
Oh, I see. You actually, yeah, okay.
Yeah, but in of it itself, like I don't know. Suppose you ask me for an obfuscated program to do something, and I give you something that does it, except for at one point, which is very hard to tell. You couldn't necessarily tell that. Maybe you think I'm a bad guy for switching that on you, but
So you can't prove that you can't tell, but
yeah, I can't prove.
Because that would be not I/O anymore.
Yeah, unless I combined it with some. So usually I/O in these proofs for using I/O, you actually do change the program. But it's kind of like the part that changes the program, that part of the proof relies on something else, like a one-way function. I'm starting to bootstrap into my head how these things actually. Yes, so you do end up changing. In the entirety, you do end up changing programs. It's just the I/O step. The programs have to be the same. So it's kind of how to use I/O.
It's an easy question. You mentioned in the proof the oblivious Turing machines.
Yeah.
Does your construction work for the class of oblivious Turing machines only, or it works, or they're equivalent
It's equivalent to the class of all Turing machines.
Yeah. Oh, okay. Good. Good. Yeah, you can make all Turing machines oblivious by like an
Log square.
yeah log. Yeah. So the simplest thing is the sweeping like a square thing, but I think there's better stuff. But we just know it exists.
All right.
Yeah, whose result was that?
Mike showed it to me in complexity class and it's on.
Yeah. So yeah, you can't simulate everything with like a log blow up, but yeah, I forgot why that does it. That's a good question though.
Does this port to RAMs? Like, is there any technical reason why it wouldn't just
Oh, like have a RAM Turing machine.
a RAM obfuscator as opposed to T?
Yeah. So the initial I think Canetti and Holmgren had some follow on. Actually, it was one of the. I'm bringing it up again, but it was one of the ones on that list of the that follow up on this. It's not immediate. The techniques do apply, and they do give you this. It's not, it needed
There's
some
a
work.
lot of work, but it's not like. Is there some new insight necessary, or is it just really just churning through?
I haven't read that paper in depth, so and especially being recorded. Yeah, I'm just kidding. I haven't read it in depth. Yeah, I haven't read it in depth, so I'm not sure what the new. I mean, I can say I tried the can it appear to me in 10 minutes test or something, and that was false. So It wasn't like that obvious, obviously. But yeah, I'm sure there's some good ideas in there. I just haven't looked at them in depth. So.
Let's thank Brent again.
Oh, thank you. Yeah.